Arvind.
Can you see me?
Yes.
Hello. Hello. No. Oh, namaste. Yes. Can you see me?
Yes. Yes.
Okay. Let me see if I get the volume here. Okay. Yeah, the Zoom is, I think, is a little bit better than this. What they have been using, StreamYard, I think it was for the other program. I remember Pregran Vigyan Prasad or something. There was a
Yeah.
Vigyan Prasad, and I did that in September, and I did it from here, and it turned out that my video wasn't working. Only I could share my slides, and people can hear me, but they couldn't see me.
They cannot see you. Yeah.
Yeah, that was the StreamYard. So I'm always a little dubious about these. The Zoom thing seems to be working okay.
Hello, Ram. Aravinda here.
Hello, Aravinda. How are you?
Hi, I'm fine. And how about you?
Thank you.
Pleased to see you virtually.
Oh, yes. I think it's a new world we're living in, the Star Trek world.
Exactly. It's morning for you, right?
It's morning, 9:30, 9:25. Yeah.
9:25. Good. Yeah.
What is it? 8 p.m. for you?
Yeah, it's close to 8 p.m. That's right. Yeah.
You've had your idli dinner?
Yeah, exactly. Well, yeah, I thought I will have my dinner afterwards.
Okay.
Yeah.
You can come to Cochin.
I'd love to. That's the point. The whole business of conferences, the attraction of conferences is traveling and food and friendship.
Yeah.
And I think all three are missing here.
That's right. Yeah, absolutely.
I see Balu. Hi, Balu.
Hi, how are you?
Fine. I think I see Kaninika there too. Hello, Kaninika.
Hello.
Hi, Aravinda.
Hi, Kaninika. Hi. Yeah, I'm glad you could join.
Yeah, thank you for letting me know about this.
Yeah.
I was just about to reply to your email, Kaninika. So while I was waiting for this Zoom connection to open, but I'll send you the mail after.
Sure.
Next Wednesday should be fine. We'll figure this out.
Okay, great. Thank you.
Yeah, you're welcome. So everything okay with you in Pune?
Yeah, everything is fine.
Okay, good. Oh, I see Peter. Hi, Peter.
Good morning. What time is it with you? Where are you?
I'm in the same time zone as you are, I think.
Okay, so
9:30.
I had to get up kind of early to talk, so I'm like a bit spaced out, but I'm looking forward to your talk.
Where are you?
I'm in Princeton, but
Okay. Well, 9:30.
Good morning, Peter. Aravinda here.
morning, yeah. How are you? Good to see you guys.
Yeah.
So, public lecture. I'm gonna watch what you do. It's tough to give public lectures. Good luck. I'm sure you'll do well. Anyway, the title looks very interesting. So,
Yeah, actually it is. Yeah, and I was intrigued by doing work on this. I started this in the summer because Kumar wanted a pure mathematician's take on the virus.
wow.
And so,
good evening.
good evening. Yes, can't hear, can't see people. So how have you been adjusting to the new world of Zoom conferencing, Peter?
Me, it's hard. I mean,
hard.
it's amazing that you can be all over the damn show and you can go to lectures and things like that. But giving one of them, well, I don't know. This is the first public one I'm going to, so it's going to be interesting because they won't let people interrupt.
Oh,
But, you know, when you give these Zoom seminars and it's a bit sterile, you know, you don't know.
no.
I gave a lecture, one lecture I gave, everybody was in the waiting room. I didn't even realize. Half an hour.
No one heard the
Somebody
lecture.
called me on my phone. So, but with a public lecture, I mean, so what's I find people, of course, don't want to interrupt, right? But it helps. But in the public lecture, well, I'm keeping out of this. By the way, when I just signed on here, you had to sign on that you're not going to that they can unmute you if you start behaving unbad, unmute you if you behave badly, which is good, I think. Yeah. Anyway.
So I see Kumar, I see Neil Koblet. Hi, everybody.
Hi.
I don't see it.
Hi, Arvinda.
Hi, Kumar.
Hi, Kumar.
Hi. I can't see everybody though.
Yeah.
Hi.
You can see me?
Hello, sir.
Oh, Balu. Hi, Balu. Yes. Good. So who starts this off?
I think Vijay, right? Vijay.
We'll start in 2 minutes.
Okay.
Mr. Armukam. Mr. Barbie. Fine.
It's unusually warm here. It's +5.
You're talking to the wrong people. They'll think it's cold.
Normally on December 11th, it's not going to be +5.
Yeah, I know.
The hospitality is warm.
It's high school.
Thank you. I would have given you Kerala spicy food had you been in Cochin.
I would have loved that. I'll take that as a brain check on that. Yeah.
Exactly.
So we have to do this again somehow.
Post-pandemic, yeah.
Yeah.
Neil, hi. This is Vijay.
Well,
Hi. Nice to see you.
Yeah, nice to see you too. Yeah. They're starting the vaccinations next week in Ontario.
Right. But it's restricted though. So.
Yeah. But at least it's a beginning.
Balu, is that an internet cord that we're seeing dangling in front of you?
Shall we start? Good evening, all of you. We will begin this public lecture. The chair of this lecture is Professor Arvinda. He is in Tata Institute of Fundamental Research, Center for Applied Mathematics in Bangalore, and also the secretary of the Ramanujan Mathematical Society. So I invite Arvinda to chair this session, introduce the speaker, and conduct the proceedings. So welcome, Professor Ramamurthy.
Thank you.
Okay. Am I audible?
Yes.
Okay. Thank you. And it's indeed a very great pleasure and privilege to be introducing the speaker of this ICNTDM public lecture this evening in India, but different hours of the day elsewhere. In particular, I believe it's morning in Canada, from where the speaker, Professor Ramamurthy, is. Professor Ramamurthy is a very distinguished mathematician and number theorist of high repute, and a very well-known and familiar personality on the Indian mathematical circuit. Born on 16th October 1953 in Guntur of the erstwhile state of Andhra Pradesh in India, a place famously known for its red hot chilies, as well as generally hot summers, Ramurthy's education and career has been in Canada in its contrasting colder climate. His love for the country of his birth and the passion of its glorious past very frequently brings him to India at least once a year, and often more than once. His ready to help and highly enthusiastic and encouraging disposition has led him to forge several meaningful collaborations with many number theorists in India, younger and older alike. His contribution to the mathematical scene in India is immense. He presently holds a Queen's Chair at Queen's University in Canada. Though I am not a number theorist, I have personally enjoyed the benefit of about a 3-decade-long friendship, warm friendship of Ram, because of his deep interest in Indian philosophy and music. However, in the year 2013, he, along with his equally distinguished number theorist brother Vijay Kumar Murthy, who is also there, and another great friend and well-wisher of mathematics in India, Michel Waldschmidt, helped to revive, after the passing of K. Ramachandra in 2011, the then 33-year-old journal devoted to number theory called the Hardy Ramanujan Journal. It was founded in 1978 by K. Ramachandra and Professor R. Balasubramaniam, who is also there in the audience. Ram, who is known for his generosity and ever ready to help a good cause disposition, is deeply rooted in the tradition of Indian philosophy. In fact, he has given full-fledged semester-long courses on Indian philosophy, resulting in a book he wrote on the topic a few years back. The honors and accolades he received are plenty, too numerous to quote here. I believe that it is perhaps one can summarize that his erudition number is 1. He's a prolific researcher, expositor, author of about 15 books, and a very popular speaker in workshops, conferences, seminars alike. A very engaging speaker. His book, jointly written with Kumar Murthy on the legacy of Ramanujan, among other of his books, is a celebrated work on the life and works of Ramanujan. Therefore, it is indeed a very appropriate gesture that none other than Ram should be delivering this public lecture on Ramanujan, number theory, and the pandemic. The Ramanujan Math Society is very grateful for him for his ready acceptance to deliver the talk. On behalf of the Ramanujan Mathematical Society and all its office bearers, I extend a very hearty and warm welcome to Ram. Over to you, Ram.
Okay, thank you very much. Let me see if I can share my screen. Can people see that?
Yes.
Okay, good. Now I'm going to keep it like that because I have a problem with the full display. So if this is okay with everybody, I'll just stay with this. Is that okay?
It's perfectly fine with me.
Okay, good. Well, let me begin by seeking the blessings from Ganesha. I want to thank the organizers for inviting me to give this talk. This is in Tamil Nadu, South India, where I was blessed by this grand elephant god. Okay, so there we are. So now the title of this talk is Ramanujan, Number Theory, and the Pandemic. And so the question that probably emerges in everyone's mind is, how are the three topics of the title connected? Well, surprisingly they are, and I hope to prove by the end of the talk that what the connections are. The connection between Ramanujan and number theory is obvious, but what Ramanujan has to say about the pandemic is not so clear, and the purpose of this talk is to explain. It turns out that Ramanujan had studied an important function now called the W-function, which plays an important role in the control of the pandemic. And it turns out to be the inverse function of the map z goes to z times e to the z. Now, we're all familiar with z goes to e to the z, and the inverse function is the logarithm function. And we know what important role the logarithm function plays in mathematics. It can speed up lots of calculations and so on and so forth. But it turns out that the inverse function of this map, z goes to e, z times e to the z, is equally important. And we'll try to cover the history behind that. Well, the connection between mathematics and epidemiology goes back to 1760, to the works of Daniel Bernoulli, who proposed a mathematical model to study the spread of smallpox. But the idea didn't quite catch on, pardon the pun, until 1902. So here's a picture of Daniel Bernoulli, 1700 to 1782. It was actually the beginnings of mathematics and epidemiology can be traced back to the works of Ronald Ross and the study of malaria. So here's Ronald Ross. Apparently he was born in India, in Almora, northern India. And he spent a good chunk of his time in India, actually. And that's where he got this idea of trying to apply mathematics to study the spread of malaria. And he discovered that mosquitoes were the cause of the transmission. And he modeled it mathematically and tried to study if we can control the various parameters, can we control the spread of malaria? And he wrote a book on this topic, which won him the 1902 Nobel Prize in Medicine. And later, along with his other students, Hammer and Ross, they proposed what is now called the SI model for the mathematical study of diseases. Here, S stands for the susceptible people, and I stands for the infected. So at the beginning, when they started this epidemiological work, they had only two functions that they were looking at: the number of susceptible people and the number of people that were already infected, and the interchange and the interaction between these two quantities. And they noted that a system of differential equations that governs the growth of these quantities. Now, I was thinking of putting these differential equations into this talk, but I thought it might just get too complicated. And so, and I'm going to discuss differential equations anyway later. I've suppressed it, but any student who's listening and is interested in this SI model, it's very simple to describe, and it's at the level of the first year calculus, basically, to study the spread of diseases using this model. In Calcutta, that's where he did his major work, Ronald Ross. In Calcutta, there's this plaque which says, "In this laboratory, Surgeon Major Ronald Ross, in 1898, made the great discovery that malaria is conveyed by the bite of a mosquito." So you see this idea that somehow to try to find the cause of diseases and then to control the cause through mathematics begins here in a serious sort of way. Let's look at the SIR model. So in 1927, Kermack and McKendrick proposed a slightly more complicated model called the SIR model. Here the letters S and I are as before. S is for susceptible people, I is for the infected people, and now R stands for the number of recovered people. So these are the three things that are three functions of time and are related by a system of three differential equations. So let S of t be the number of susceptible people at time t, I of t the number of infected people at time t, and R of t the number of people who recovered at time t. Then the first quantity, how does the number of susceptible people change with time? Well, it depends on the interaction between the susceptible people and the infected people. And the interaction is measured by the product of the two functions times a certain rate, beta. Beta is the infection rate. And then, of course, we have the recovery rate. So the number of people that recover is a certain proportion of the people that are infected. So we will define, we write down the differential equation, dr of t by dt is equal to gamma times I of t. So the rate at which the recovery is changing is proportional to gamma times the number of infected people. And now the middle equation is, of course, the key. The number of infected people is the rate at which that changes is governed by this differential equation beta S of t I of t minus gamma times I of t. So this is basically the system of three differential equations, and these three functions are not independent, they're interrelated by this very simple looking equations. Now, if you try to solve this system of equations, you'll find that you'll run into trouble. So which is what exactly happened with Kermack and McKendrick. Here's Kermack, and there's McKendrick. So with Google these days, you can find these people. You just have to find the right people, though. You shouldn't put put the wrong pictures down. But fortunately, these are the right people. So let's try to solve the Sur equations. Let's look at them again. And now, if you stare at these equations, you'll see that the first equation divided by the third equation will get rid of the I of t function. So when you do that, you can simplify the equation, and you get an equation ds of t by dr of t is equal to minus beta over gamma r of t, and then you can solve that very easily just by integration, and you find that s of t and r of t are related. So the way that s of t grows is s of 0 is the number of susceptible people at time 0, and it's equal to e to the minus beta over gamma times r of t. So this is already an interesting find. And then we have to keep in mind that we're going to think that the population of the group is constant with time. You could vary this modeling by introducing more complicated, make population vary with time. But for the purpose of this discussion, we'll just keep it simple, just like Kermack and McKendrick actually did. They just said, well, let's just make sure that no new people come into the group and keep the population. So S of t plus I of t plus R of t is now equal to n. And now if you insert these two things into the third equation, so let's see, if I move this cursor, do you see? Can people see when I say this, when I do this? Yeah, okay, good, that's good. So dr of t by dt is gamma I of t, but I of t is equal to n minus r of t minus s of t. So I put that in, gamma n minus r of t minus s of t. But now s of t, we solve for s of t, so put that back in. So you get this equation, dr by dt is equal to gamma times n minus r of t minus s of 0 times e to the minus beta over gamma r of t, which is the basic differential equation governing the behavior of the epidemic. Now, this quantity beta over gamma is very important. It figures in many of these calculations. So let me just try to explain that. So let's look at this. Let's look at this equation. If you try to integrate this, it turns out that you can't. It's not an elementary function. So Kermack and McKendrick were forced to approximate the exponential function by a quadratic polynomial. So as I mentioned, the spread of the pandemic is determined by this quantity beta over gamma. Remember that beta is the infection rate and gamma is the recovery rate. So this quotient is often designated as R0 in the literature of mathematical epidemiology. And it's called the basic reproduction ratio. And if this ratio is bigger than 1, you have an epidemic on your hand. And apparently, at early March, this ratio was somewhere about 6. So you can see this COVID-19 was a serious thing at that time. So using our notation for R0, let's simplify this thing. Our differential equation now becomes dr by dt equals gamma times n minus r of t minus s of 0 times e to the minus r0 times r of t. And so their idea in their, by the way, I recommend the reading of the 1920s, that's, sorry, my mail program. I recommend the reading of the Kermack-McKendrick paper because it's actually quite readable. It's got a wealth of ideas, which I think still can be used and researched further even today. So anyway, they look at the approximation of the exponential function by this quadratic polynomial. So you all know the exponential function, e to the x is equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial. It has an infinite series. So what they do is they just ignore the cube terms and higher terms and just approximate it with the quadratic polynomial, and they get a manageable thing. So essentially, when you strip all the functions together, I mean, instead of being overwhelmed by notation, we just have a simple equation here. Dr by dt equals gamma times a plus br plus cr squared, where a is this n minus s of 0, b is this r0 term, and c is the r0 squared, s of 0 over 2 term. So now everybody would recognize, hey, this is first year calculus, and indeed it is. You integrate and you end up at the inverse of the hyperbolic tangent function, which is what they did. Okay, so if we do that, you get something like this, and then you go back and you see the novelty of the Kermack-McKendrick paper was that it modeled the spread of the disease via 3 differential equations and gave an approximate solutions, which was then corroborated by actual events, and the error was not too large. They actually tested this on various other diseases that came about. By the way, notice that much of this work is after the 1918 pandemic. The last pandemic, the Spanish flu, as it's called, occurred in 1918. And at that time, this model wasn't there. So you see, it's another interesting theme. I mean, from a philosophical angle, you see how mathematics can be used to control our own life and kind of, you know, we're not victims of events, but we can actually shape the events. And so here's the beginning of something really profound. So in that, they knew that their solution was not exact, but then they never bothered actually checking how big an error they commit. Believe it or not, as far as I could tell, the first calculation of the error term was done by Kumar and myself in the summer when we started to look at this paper very carefully. In their work, they were able to predict that any pandemic often has a peak, and one can foretell when it will occur, given the initial parameters and the reproduction ratio. So R0, remember, was the reproduction ratio. It was determined by the number of the rate at which people were getting infected and the rate at which people were recovering. You needed that knowledge. And then you need to know some initial parameters, how many things are there at the beginning. And then once you have this, you can predict when this pandemic was going to peak, how many people were going to die before the peak occurs, and how many people were going to die after the peak occurs. And all this information is quite useful in trying to control the pandemic. So the final solution, here it is in their paper. It turns out that it's equal to R of t, the number of, remember what R of t is? R of t is the number of people that recover at time t. So R of t then is equal to this R0, which is that reproduction ratio, S of 0, the number of susceptible people at time 0, minus 1 plus square root delta, which is this discriminant function here, hyperbolic tangent of square root delta over 2. Let me try to off my mail program here. Sorry about that. So it won't make any more noise. I hope I've not lost people. Okay, so can people still see this? Okay. If you can't, just let me know. So you have this. Okay, thank you. Yeah. So you have this R of t given by this rather innocuous function, just a hyperbolic tangent function, and then you have this phi, which turns out to be this quantity here, and using this they were able to now go back and check what. Now that I know R of t, I can now figure out I of t being the number of people which are infected at time t. And then it becomes this hyperbolic secant squared function. And the function appearing in the above theorem is often called the epidemic curve. And it is a symmetric bell-shaped curve that reflects what is often seen in epidemics. namely that new cases continue to rise until they hit a certain peak point and then slowly reduce in number. And let's note that this model does not take into account variable rates of infection or removal. One can, for instance, drastically reduce the rates of infection by following the usual guidelines that people have been repeating ad nauseum all over the world, basically guidelines for personal hygiene, mask wearing, and social distancing with or without a vaccine. That's the way you control it when you don't know how to control all these other parameters that might be playing a significant role. And but now that you have a mathematical model and you know where the things are going, the peak is going to occur, you can try to control some of these other parameters. One of the ways of taking these social guidelines that have been suggested, something's happening. I'm not doing that. Are people seeing some red scrawls?
I'm seeing some red spots. Yeah, that's true. But I don't know why it's happening. And now it's gone. Yeah.
Okay. I wasn't doing that. Anyway, so that's what you have. Now, interestingly enough, the question then is error terms in the Kermack-McKendrick solution. So that was the question that Kumar and I asked ourselves in the summer when we started working on this thing. What is the error incurred in a quadratic approximation? And it turns out not to be significant if a small constant is added. So let me just state the theorem. It turns out that the exact solution for R of t in the SIR model satisfies pretty close to what they got, except that you have to add some constant which we give in terms of a certain integral. And then there's this O of 1 over t term, which is the error, of course, which as time goes to infinity, this goes to 0. So basically, this is pretty exact. It's not quite exact, but there's a very, very small error in the original Kermack and McKendrick solution. The reason I say this is because there were a bunch of papers written in the 1950s, which I will discuss in a second, which try to say that the Kermack-McKendrick solution is off. But the point here is that it's not off by a lot. It's off, certainly true, but it's not off by a lot. And so the question of trying to get the exact solution was a major problem for research in mathematical epidemiology in the 1950s and the 60s. So that's the only correction that you need to make is this small constant phi prime, and then you have this error that goes to 0 as t goes to infinity. Now, in the 1950s, 1956 to be exact, Kendall, here's Kendall, D.G. Kendall, started working on trying to find an exact solution. Of course, you know, if you know anything about Galois theory and Galois theory of differential equations, which is basically called the Picard-Vessio theory, I'm seeing scrawls. Maybe is everybody given permission to write on the thing, or I don't know how that's working. It's a mystery to me. But anyway, so Kendall, I think, was trying to see if you could actually solve this in closed form. And as far as I can make out, I don't think there's any paper in the literature that actually shows you can't come up with an elementary function that's known. But I would suspect it's a nice exercise for any graduate student listening here to apply the Picard-Vessio theory to show that that solution of that differential equation is actually a transcendental function. So he defines begins by defining a transcendental integral. Instead of trying to solve for R of t, S of t, and I of t, you just solve for t. And the parametric solution that Kendall provides is that t is equal to this integral. And this integral is actually one of these transcendental integrals. So you have that. And then he notices that this integral makes sense as a function of a real variable, provided you restrict your r, the r in the integrand, to lie between two real numbers, minus zeta 1 and zeta 2. And minus zeta 1 and zeta 2 are the unique negative and positive roots of this equation, this exponential equation. I of 0, remember, is the number of infected people at time 0. And R0 was the reproductive ratio. And so zeta is an unknown. And you try to solve this equation, solve for zeta. And it turns out, it's a very simple calculus exercise. Something is happening to my screen. Are the permissions, can I ask the organizer to check the permissions? Can I ask the organizer to check the permissions, please?
I'll ask Vijay.
Okay, thank you. So, so you have these two roots, zeta minus zeta 1 and zeta 2 are the real roots. I'm not doing this, by the way, again. So if you people don't mind, please remove these permissions. So this leads us to study roots of exponential equations. And so this is where the Lambert W-function comes in. Exponential equations and the Lambert W-functions. So if you want to solve for R, you have to really start studying. I'm not doing this blue lines, by the way. Please, can you, somebody is this what
I'm checking I'm checking, but yeah.
Yeah, this is what they call Zoom bombing or something. I don't know what, you know. Yeah, so anyway, you look at this function x e to the x and you plot it. Now, as I said, this is to be thought of as function like the exponential function, which is you know, e to the x, and but not quite the same. And here you see the function has two real branches. The inverse function has two real branches, and so the inverse function is what's called the Lambert function. So what is an inverse function? So supposing I give you a function f of x, we say g of x is an inverse function if f of g of x equals x and if g of f of x equals x. So this is the most basic intuitive definition. So the problem with the definition is that the domains and the ranges have to match up. So for example, here you have a function a goes to 3, b goes to 1, c goes to 2. The inverse function is the map that goes in the other direction. 1 goes to b, 2 goes to c, and 3 goes to a. So that's basically the notion of an inverse function. But when you get down to real life, it's a little bit more complicated than that. When you have you know, continuous regions, it's a little bit more complicated. For example, if you study functions on the real line, you will see that the simplest way to understand the inverse function is to think of your function here. You see the function here, is a function in red, it's moving up like this. And then what you do in order to get the inverse function is you take the line y equals x, that's this dotted line here, and you reflect f of x using that dotted line as a mirror. And then you get another function which you would call f inverse of x. I mean, that's from the standpoint of real variables. We'll come to complex variables in a second, but basically that's the idea. And when you do that in the case of the map x goes to e to the x, it turns out that this is Lambert's contribution to mathematics. In 1758, he was trying to solve trinomial equations. And there's an extensive correspondence between Lambert and Euler. And then they come up with this, well, they don't call it the W function, it's called the W function only. Believe it or not, it was called the W function as late as 1980 or something. Anyway, this is where it was introduced, but then people then forgot about it. So we're, as I said, mentioned at the very beginning of this talk, we're familiar with the logarithm function, which is the inverse function of x goes to e to the x. But the W function is the inverse function of x goes to x times e to the x. And then so when you reflect on the line y equals x, that picture that I drew in the previous slide, you see that this becomes something like this. And you can see that for x positive, there's a unique value here. But for x between 0 and minus 1 over e, you can see that there are two values. So it's you see, so there, this means that what are called branches of the inverse function, there are two values. So you really need to look at, there are two real branches. And the question from a complex analysis perspective is to try and understand what are the complex branches, just like you would try and do that for the logarithm function. So this is really all about the game of the name, which is what I say about this brings us to an essential aspect of the philosophy of mathematics. And as we all know, the number system is built out of the discovery of zero. You may ask, what's in a name? Well, there's a lot in a name. Earliest known evidence for the decimal system goes back to inscriptions in Indian temples dating back to 100 CE. Best known is the famous Vishnu temple in Gwalior, Madhya Pradesh, where you see the number 270 there, clearly inscribed on the temple wall. And the idea here is, what is the significance of zero? Well, the significance of this, what did you do? You gave a name to some airy nothing, as it were. It's nothingness. You gave a name, and that changed the world. So somehow, the game of the name is at the heart of knowledge. And that's exactly what we are talking about here. The logarithm is a function which was very useful, and we know how useful it is. The inverse function of the exponential function is the logarithm function. The logarithm function has a familiar power series. Log of 1 minus x is the usual. Minus log of 1 minus x is usually x plus x over 2 plus x over x cubed over 3, dot, dot, dot. So you have a power series. And the question now is, it opens up other bunch of questions like analytic continuation of the logarithm. And we all know that this is not a trivial matter in complex analysis. You have to start talking about branches, analytic continuation, and so on and so forth. And it turns out a similar theme emerges. I didn't put that mark, okay? I have to keep on, I didn't do that. A similar theme emerges for the W function, and it looks like Ramanujan had studied it. Yeah, are you seeing that mark? It's not, it seems to me.
Yeah, I'm seeing
it seems to me some child is scrolling over an iPad or something, and a screen, it seems that the screen is being shared by somebody else as well. I don't know.
Sir, we have blocked everything. We have blocked everything. I don't know why this comes.
Oh, okay.
Okay, sorry.
Okay, thank you. It's okay. So now we come to Ramanujan and the Lagrange inversion formula. So the general question first studied by Lagrange asks if f of x is a given power series expansion, what's the power series expansion for f inverse of x? That's basically Lagrange inversion formula. And Lagrange answered this question. It looks like Ramanujan had rediscovered it and applied it to determine the power series of the W function. So here's Lagrange's theorem. Suppose f of z is an analytic function in a neighborhood of 0, with f of 0 equal to 0 and f prime of 0 not 0. Then f inverse is analytic in the neighborhood of 0, and the coefficient of z to the n in the power series expansion of f inverse of z, that's what the left-hand side here means, is equal to the coefficient of z to the n minus 1 of the function z to the n over n f of z to the n. It's a beautiful theorem, actually. And in our paper, in the paper that Kumar and I wrote, we give a short proof, but that proof is not our proof. I found the best proof, essentially a two-line proof of this in the Whitaker and Watson's classical book called A Course in Modern Analysis, written at the early 20th century. It's a beautiful proof. It's basically 2 lines if you use complex analysis very correctly. But now you can see why this theorem is of value to us, because you see, we want to apply this with f of z equal to z times e to the z. Okay, so imagine in your mind, f of z is now z times e to the z. If you put f of z, z times e to the z, when you take the nth power, the z to the n's cancel, and you get e to the minus nz here, and you know what the coefficient of z to the n minus 1 is of e to the minus nz. It's n to the n minus 1 over n factorial. And that's exactly what Ramanujan does. He finds out that the Lambert function, the inverse function, we'll call it W0 for a moment, is minus n to the n minus 1 over n factorial z to the n. And this power series converges absolutely for mod z less than 1 over e. For those of you who are in the audience who are first year undergraduate students, this is an interesting exercise to do. Power series, you apply the ratio test and it's basic calculus to check that the series converges for mod z less than 1 over e. So this is the inverse function of the Lambert function. And obviously, there's a problem here. It's not defined for all values of z, and there's a problem. But remember in the picture earlier, we thought there were two branches of the inverse function. And for z positive, you had a uniquely defined value. So you would like to get an expression, a series expression, which is valid for all z. And that's an interesting problem. Surprisingly, I mean, unless you start doing research, you never discover these things. Surprisingly, that the analytic continuation for all z with a series like this was done only recently as this year. I'll talk about it in a second. So if you're familiar with Ramanujan's collected papers and you look at question 738 on page 332 of his collected papers, he asks one to show that if 0 is less than x is less than 1, then x is equal to this function. That's basically the same thing. We've written W0 because like the logarithm, the W function has many branches, and Ramanujan discovered only a part of the principal branch. So what do the branches of the W function look like? There are two problems that emerge from what is the problem of analytic continuation. If you don't understand what analytic continuation is, suffice it to say that you'd like to think of it as a function of a complex variable, and you'd like to define it for all real numbers and all complex numbers as well, in a reasonable sort of way. That's basically the idea behind analytic continuation. And the next thing is, of course, somebody has raised a hand. Professor Thangaraj has raised a hand. Any question? Could you?
Yeah, I see somebody called Madhav Panikar. Is it possible to include reasons other than the interaction between S and I?
Oh, yeah, well, that's a good question. I'll come back to that at the very end. Yes, we're trying to keep, the SIR model tries to keep it simple. At the beginning, I'm just following the Kermack-McKendrick thing. And I believe the later models, and Kumar might be able to, because he's been on this task force on the COVID-19 thing, advising the Ontario government. So he might be able to tell more things, but there are further, more elaborate models that people have been using, and that's the problem for research in epidemiology. So for now, as I said, this lecture is basically, as I said, subtitle is Epidemiology for the Pure Mathematician. So we're trying to look at this function and the context in which it has on the SIR model. So now the question of series expansion, surprisingly, both of these problems were solved only recently. The analytic continuation, so here are the branches. So the principal branch is defined on this region of the complex plane. And then you have all these other branches, you see, just like the logarithm function. And this was done in 1996 by Corliss, Gonnett, Hare, Jeffrey, and Knut. Now, if you recognize some of these names, you'll recognize also that they are all computer science people. And this is exactly where the W function arose as a critical function to be studied in the context of computation. And then they realized that it had to be named. And they were the ones that named it as the W function. Actually, they chose the letter W because E.M. Wright, the famous collaborator of Hardy and Wright, apparently devoted quite a chunk of his life to the study of the W function. So the W really stands for Wright, of Hardy and Wright. Okay, Now, the question of coming up with a series expansion is actually a recent paper by Beardon called the principal branch of the Lambert function, and here it is. So here's the infinite series expansion. W0 is equal to m going from 1 to infinity, sum a sub m times this quantity, square root ez plus 1 minus 1 over square root ez plus 1 to the power m. And a sub m is given by this finite sum, which has that Ramanujan coefficient there, but it's got this extra binomial stuff. So this is an amazingly impressive, and this converges for all z in this region. So this is the principal branch of the Lambert function given as a power series, and it was solved only as recently as this year. I have no idea what was the motivation for Beardon to do this, but perhaps he was also aware of its connection to the pandemic. He also indicates in the same paper how one may derive similar series representations of the other branches. And again, if this, graduate students are listening to this talk and have some interest in complex analysis, then I would urge you to read this paper, which is not a big, long paper. It's really readable. And when he just says, oh, you could derive other representations for the other branches and doesn't do it, I think one should really do it and see what other interesting features come up. Now let's go back to Kendall's exact solution. Remember, Kendall was trying to come up with an exact solution. He tried to determine the peak of the pandemic, and he noticed that it reduces to determining roots of that exponential equation of this form where we had A, B, and C. I'm not going to write those things down, but if you look at the previous slide, A, B, and C were given in terms of the initial parameters. And now, here's how you would do it. This is almost like taking logs of both sides type of thing, almost quite that, but not quite, but and kind of fun. And so here's how to do it. And I want to put this in detail because it's a public lecture and I'm sure everybody can follow it. So what you want to solve for R. So what you do is you take the e to the minus CR to the other side. And the nice thing about e to the exponential function is that when you multiply the inverse, you get something like this. So this is a neat little equation. And now you fudge it. You fudge it by introducing an exponential factor to e to the minus AC over B to both sides, and then you rewrite this thing. And now the key idea is, why did we do this? Well, you look at this. This looks like x e to the minus x. That's what it looks like, doesn't it? This looks like this looks like x times e to the x. That's what we're trying to. So this is something x times e to the x equals that. So therefore, now you apply the inverse function, and you see that all the roots are given by minus a over b minus 1 over c w sub k of c over b e to the minus ac over b. So therefore, just like in the log function, you get infinitely many roots, you are going to get infinitely many roots here as well. Now keep in mind that the inverse function has 2 real branches, so you're going to get exactly 2 real roots that Kendall was talking about. Oops. Okay, so sorry, I scrolled down. Okay, the real roots. So only 2 of these roots are real, the others are non-real. The 2 real roots appear in the Kendall's exact solution, and they are given in this way. So the 2 roots are what? Well, they are that R0, that reproduction ratio, I of 0, that number of people infected at time 0, times W0 times this quantity, which is an exponential of something. So it's a transcendental argument. And these are the 2 roots. And the meaning of these 2 roots, according to Kendall, is that the first root represents the number of people infected before the peak, and the second root represents the number of people infected after the peak. And therefore, the total number of people infected is given by the sum of the 2 special values of the Lambert function on these 2 branches, one the 0 branch and the other -1 branch. So you get an interesting, amazing kind of connection. And anybody starts seeing the zeros of a certain function have significance to the pandemic is kind of intrigued by this because of the analogy to zeros of the zeta function or zeros of L functions and so on and so forth. So synopsis of events. So far we've discussed the SIR model of the epidemic and the approximate solution given by the 1927 paper of Kermack and McKendrick. In 1956, Kendall gives an exact solution that involves the Lambert W-function. By the way, I want to point out, in the same Kendall paper, he uses a calculus of variations argument to show that the Kermack-McKendrick solution is off. Of course, we know it's off, but as we're trying to point out in our paper, it's not off by much. And then you have this other feature. And in 1996, Corliss and others give the analytic continuation of the W function, show the existence of a countable number of branches similar to the log function. And in Ramanujan's second notebook, written in around 1903, we find the rediscovery of the Lambert function and the development of the power series expansion. Finally, in 2020, Beardon derives the power series expansion of WZ valid for all Z in the principal branch. So recent work with Kumar on special values of the Lambert. Now that we've understood it from that perspective, then the pure mathematician in us kind of took over, and we started wondering about the Lambert function in its own right. You know, why treat it with importance just because it appeared in the pandemic? It's important on its own right. So it seems to have arithmetically interesting properties. So let me kind of share with you one of them. If alpha 1 to alpha n, I just cut and paste from the paper. So corollary 17 is a thing in the paper. Anyway, so if alpha 1 to alpha n are non-zero algebraic numbers and C1 to Cn are rational numbers, then at least one of the following is true. The C1 W alpha 1 plus Cn W alpha n is either 0 or a transcendental number. And the product of W alpha 1 to C1 W alpha n to Cn is either non-zero or transcendental, where W is any branch of the Lambert function. I'm not going to go into the proof, but it's actually a simple application of the Lindemann-Weierstrass theorem. And why I put this in front of you is because it seems to suggest that there should be a parallel theory with the W function to Baker's theory of linear forms and logarithms, which may have applications. So here's some nice corollaries, which you can explain to first-year calculus students. For any positive algebraic x, so x is this argument in the integral here. For any algebraic x, these integrals are all transcendental numbers. It turns out they're all special values of the Lambert function. And now I don't want to, I know it's a public lecture, but there are experts sitting in the room. Therefore, I just thought I'd flash this. If you shove in a famous conjecture of Shanuel about the transcendence degree of the exponential function, and you look at it and see what consequences it has with the Lambert function, it turns out that the theory, the Baker's theory of linear forms and logarithms should be true modulo Shanuel. So Shanuel already predicts it, and therefore it's probably a good research project to pick up Baker's book on transcendental number theory and see how far you can push it to the W function. And the other point that enters into this talk is the use of Bell polynomials. So the W function leads to an explicit power series expansion for the solution of the SIR system of differential equations. So here's the idea behind Bell polynomials and inverse functions. So if I have f of z equal to a power series, then what is the power series for e to the f of z? Well, it turns out e to the f of z is going to be again another power series. But what is that coefficient? And that coefficient is what's called the Bell polynomial. And it'll be a function of the first n, C1 to Cn. And if you look at that, and then you try and study these exponential polynomials like this and write down its Hadamard factorization. Remember, we already recognized that the roots of exponential polynomials are special values of the Lambert function. So the omegas here are really special values of the Lambert function. And so you have this nice Hadamard factorization. And so when you plug it back in, you can actually write down the exact solution in terms of power series expansion. So when we do that, let me not get too bogged down, but I think at least the experts in the room can recognize this. The students, the graduate students and the undergraduate students can probably work this out at home once they get the idea. So once you have these exponential polynomial in terms of these roots of the Lambert function, you can write down this, this 1 over that in terms of a power series. And then you end up getting an expansion of 1 over A plus BR plus e to the CR in terms of the Bell polynomials. And then you integrate it, and now you stick this back into the Kendall solution, and you see that the coefficients of the power series are really special values of these Bell polynomials evaluated at the special values of the Lambert function. So let me summarize. The SIR model of epidemiology leads to a system of differential equations whose solution gives rise to a new transcendental function called the Lambert function. And surprisingly, this function was studied by Ramanujan in 1903, as entries from his notebooks, both lost and found, show. And the study of this function from a complex analytic perspective and a number theory perspective seems to open a new cosmos for us to explore. So if we're able to see this far, it is because we are standing on the mountain peaks of mathematics. Thank you for your attention.
Thank you. Thank you very much, Ram, for this wonderful exposition and leaving with a lovely photograph, the majestic Himalaya. I invite questions. We have time for, I think, for a couple of questions, if there are any. And there was, of course, one question during the talk, which I mentioned, I think, and I don't know if you want to take that first.
I don't mind. I mean, what was the question again?
Yeah, I'll read. I think is it possible to include reasons other than the interaction between S and I? This is the question.
Yeah, I think I answered that to some extent, that there are more models, the SIES model and so on and so forth, that you can probably open up a book on mathematical epidemiology and see that there are more things that can be introduced. Absolutely. But I think the point is, before we introduce too many parameters, you have to understand how these other things are working. And I think that's the greatness of the SIR model. If I understand things correctly, I mean, I've been looking at books on epidemiology, and I see that essentially it's the SIR model that dominates the show.
Okay, thank you. Are there any questions from the audience? Please feel free to ask. We have time for a couple of questions.
May I ask a question?
Yeah. Prasad, please go ahead.
Yeah, this is Prasad. Thank you for the most amazing talk. It's extremely timely and understandable. Thank you. That was fantastic. The technical question is, so for the peak, is there an expression, approximate or exact expression as to where the peak happens?
Yes, because I gave that function I of t in terms of the secant squared function, and that's just a function, first-year calculus function. So in order to find the peak, you just differentiate and set it to zero and solve for that, which is what they did, which is how they did it. Yeah.
And maybe if I can follow up with one. Yeah. So from my understanding, the more challenging version is the multi-parameter one, where we don't have a single set of equations, but we have a matrix version of it. Is that correct? So I guess given some of the research is so recent, even for the single variable version, so to speak, for the matrix version, I'm assuming much less is known, but I don't know if there are any pointers in your paper or other literature you can suggest.
There are no pointers in our paper, but we certainly allude to the fact that there's more work to be done. We did reference a few expository papers that might have that discussion, but I haven't checked it. I agree with you that the matrix version is obviously something that one should pursue. Some sort of matrix version of the Lambert function is already incorporated by the computer scientists. At least that's what I found. Yeah. So you're absolutely right. Yeah.
This was wonderful. Thank you so much.
You're welcome.
Are there any other questions from the audience? I see two in the chat box. Shall I read it out for you, Ram?
Absolutely. Yeah, absolutely. I'm not looking at the chat box. So.
Okay, okay. Yeah. So there are two questions. I'll read them both. Perhaps I don't know if you can, if there are any connection. It's from one question is, are there any applications of the function WZ in integral calculus? And the second question is, can I read both of them?
Yeah.
Yeah. Second question is SAR model the motivation behind studying the W function? What are the applications of W functions in general? So since both were related W functions, I thought I'll put them together.
Yeah, that's a good question. So yes, absolutely. I mean, the W function is just the inverse function of Z e to Z. And so that will have applications. So you see, every time you have e to the x equals y, you solve for x as by taking the logarithm. So anytime you have some sort of exponential equation, you will solve for it, and you can write it down in terms of the W function instead of approximating it. It's a transcendental function in its own right. And that's the point. And I think from that perspective, you know, every time a pure mathematician meets a new transcendental function, that's like another cosmos to discover. So it just tantalizes the researcher. So there's lots and lots of applications, not only in calculus, but, you know, just like the logarithm function is applications, not just in calculus, but in number theory and so on and so forth. So that was the purpose of my introduction to that thing. As far as the W function arising from the SIR model, no, the W function existed well before the SIR model. It's just that the people who were studying the SIR model perhaps didn't realize that there was this function, and it was only recently, like in the last 30, 40 years, that people started realizing it's there. I mean, Kendall doesn't talk about the W function, but Kendall recognizes that the roots of that exponential equation are governing the number of people who are infected before the peak and after the peak. He realizes that, but he doesn't talk about. His main point in his paper actually is to show first that the Kermack-McKendrick model is off the mark. And it's actually a nice paper. He shows that using a calculus of variations argument. And then he's trying to get an exact solution. And I think it's that exact solution so he can't get it. So he writes this thing down in parametric form and changes it. And I don't think there's really any solid paper which says that, no, there's no point in trying to get an exact solution because it's not an elementary function which is known. I mean, I think a paper using the Picard-Vezio theory and showing that this cannot be written in terms of earlier elementary functions is not a bad thing, suitable for the American Math Monthly or something like that. That would be a nice paper to write. Does that help understanding? I mean, the Lambert himself introduced his function to study trinomial equations. Supposing you have a trinomial equation is x to the a plus x to the b plus c equals 0. So you want to try to find the roots of that thing. And he noticed that those polynomial equations, although you have to go back in time, you know, put yourself romantically back in the 18th century and see what these people were trying to do. At that time, polynomials were the craze of the day, and you were trying to find formulas for roots. I mean, so whether before Galois theory, you know, is there a formula for the roots of general equations? And of course, there's no general formula after the 5th degree. So, but then Lambert started noticing for trinomial equations, you could kind of write something down, which is reasonable. And Euler followed suit and studied this. So there are all these other applications of the Lambert function well before the SIR model. Does that help?
Yeah. One question I would like to put is the final solution? Yeah.
Would it be, so sorry for disturbing, I think I'm told that it will close at 9 o'clock. I don't know, Vijay. But
Okay.
Ram, to answer your question, I think both the people who had asked the question say thank you very much. Yes, yeah.
Oh, you're welcome. So should I stop sharing my screen?
I think I should. Well, I mean, you could keep the screen on, but I think we should end it up because I think that's what Vijay has been messaging me. So thank you very much once again for this wonderful, wonderful talk. I think people who want to ask questions can definitely, privately ask Ram. he ever, ready to do that. Okay, thank you very much. And Vijay, if you want to say a few words, that's fine with me. I am done. Yeah.
Okay, thank you, Aravinda and Ram, for their for the talk. It's already 9 o'clock here in India. So good night, good morning, whatever it is. And see you tomorrow. The plenary talk starts at 9:30 a.m. tomorrow. Bye.
Okay, thanks.
Thank
Goodbye.
you. Thank you. Bye.
Yeah.
Now, if the